Log on, tune in, find out. Another good idea from Cambridge.
It's a pleasure to have Axel Kleinschmidt, who's going to tell us about infinite discrete symmetries and its singularities and modular forms.
Okay, thank you very much to David and Neil and the other organizers for the invitation to be here. I'm very much enjoying my stay, having good discussions. And today I will talk about some work that I have done and am doing with this list of people here. So mostly with Hermann Nicolai, Jakob Palmquist, and the students Philipp Fleig and Michael Köhn. And so the work touches on many different topics or ideas which have been around for many years, and I can only give a very incomplete list of references here, but I wanted to tell you sort of which topics I'm touching on. So the first topic is the subject of cosmological billiards in supergravity and hidden symmetries. This is something that goes back to the ideas of Belinsky, Khalatnikov, and Lifshitz in the 70s and was revived around the year 2000 by Thibaut Damour and Marc Hainaut. And I will review what role this plays for what I'm trying to say. It also touches on the study of mini superspace models. So whenever you try to quantize gravity, I mean, there's the problem that the space of metrics, which is the space that you would like to quantize canonically, is infinite dimensional, and the metric on that space is very complicated. So people for a long time have thought about studying sort of toy models, which are these mini superspace models. Superspace has nothing to do with the supersymmetry here, which are truncations of this infinite dimensional space of metrics. And they appear, for example, in cosmological applications. So this is also something that will be relevant, of course, because there's also cosmology appearing here. And as a final point, I will try to make some contact with U-dualities as they have appeared in string theory, or more particularly string scattering amplitudes. So this goes back to work in the late 70s by Michael and many of his collaborators and other people. So the plan of what I'm trying to say is, first I will give you some review of these cosmological billiards, how you get from there to symmetry groups, how you get to discrete symmetry groups, what you have to do if you want to think about quantum gravity in this language. We will see that there's some very nice arithmetic structure that appears, and that will feed back into all the objects that you need to describe these cosmological quantum billiards. This will be then the context or the content of the third part, which are modular forms for hyperbolic Weyl groups. And finally, I will say something about infinite Chevalier groups and automorphic forms for them, and then I will discuss some open problems. So, a lightning review of what is a cosmological billiard. As I said, this goes back to BKL in the early 70s. And it rests on the idea that when you have supergravity or any gravity theory near a space-like singularity, which I've depicted here, sort of there's a slice t equal to 0, which you can think of as the Big Bang if you like, points which are very close to this initial hypersurface, space-like hypersurface, if you're not far away, it can happen that the light cones of 2 points do not intersect in the past. Of course, this is a general phenomenon, and this means that as you get closer and closer to the singularity, spatial points that are distinct, they get decoupled. So in the extreme limit, when you go to the singularity really itself, there's no causal interaction between neighboring points. And this is sort of at the heart of this BKL conjecture, that you can describe the dynamics in the vicinity of the singularity by something which at lowest order in the approximation is ultra-local. So there's no interaction at all between the points, everything is just dynamics in time. Of course, I mean, the conjecture goes a bit further and says there's a systematic expansion of the dynamics which rearranges the partial differential equations of Einstein in terms of ordinary differential equations in time in some kind of Taylor expanded manner. But for the cosmological billiard, all we need is this sort of crudest approximation, which is ultra-local dynamics near the singularity. And to study then this ultra-local dynamics near the singularity, what you have to do is you have to go to some adopted frame for the metric, or this is one way of doing it, where the important content now is here in these variables beta a. So this beta a is the size of the 8th spatial direction, so there's one time direction and d spatial directions here, theta A is some frame on the spatial part, and beta are just the sizes of the different directions. And it will turn out that as you go to the singularity in this limit, everything that is important is the size of the spatial directions, and they will change the closer you get. And we're interested in how the sizes change as you approach in the singularity. No. So you can start from sort of a generic universe, and then you want to study its development as you go to the singularity. So the different directions will scale in different ways, and you want to sort of have a dynamics for how this universe then behaves when you go to the singularity. And one of the main insights by BKL was that this is actually a chaotic system. So it's not like it will go to something that is point-like, or where all the sizes go to zero. They will just change in a random manner, these radii.
So these apply when you reach the singularity of the Schwarzschild black hole, for example? Or
yes, so this is for a generic spaceless singularity like the one in the Schwarzschild black hole. Yeah.
And if you have a rotating black hole or something like this, do you have this behavior appearing at the Cauchy horizon? Or
so this is not at the horizon, this is really at the singularity, and what you need is a space-like singularity.
It does not apply for...
Yeah. So it doesn't apply for branes, for example. So if you go through the analysis and try to find the effective Lagrangian that you get for the scale factors beta A for the radii, or logarithms of the radii, you find that there's some kinetic term with a metric here, which I call GAB, which is just a set of numbers, it's constants, and there is some effective potential for these scale factors. Now the important point is that this metric here is really the truncation of this infinite dimensional de Witt metric on the space of all metrics to these diagonal metrics, and most importantly it has Lorentzian signature. And then there are some potential terms for the betas, which are typically of exponential type, but when you get closer to the singularity, what happens is that these become infinite potential walls. So either you're on one side, the potential is zero, you're on the other side of the wall, the potential is infinite. And if you want to sort of draw a picture for that, here is the space of scale factors, beta, and I've drawn a light cone because it's a Lorentzian space. And what the effective potential now will do is it will put in hyperplanes. So either you're on one side of the hyperplane or on the other side of the hyperplane. And what you have to look for is sort of the smallest space inside all the hyperplanes where the potential is zero. And this is some region, which is typically of some conical shape that I've indicated here. And you can then ask questions about the geometry of that space, because this is the only space, so this is the only part of beta space where motion is allowed because all the potentials are zero. And the geometry of that space is of course given by the inner products of the normal vectors to all the hyperplanes. And in the particular case of d equals 11 supergravity, what you find is that the geometry of that space is identical to that of the Weil chamber of some hyperbolic Kac-Moody-Lie algebra, which is called E10. So here we see some group theory. This is like the Weil chamber for some group, but now the group is not one of the groups that you normally study in the finite dimensional case, but this is the Weil chamber of some infinite dimensional group. And typically in general, the shape of this region here depends on the matter content, depends on the dimension, but I will mostly restrict to the case of maximal supersymmetry, and then all you have to know is that this is related to this group E10. And something that is important about this group now is that this chamber here has a finite hyperbolic volume, and that's related to chaotic behavior as you approach the singularity. This is similar to what you would find for pure gravity in 4 dimensions. So this is the classical and old story about cosmological billiards that you might have heard about somewhere else. Now, what I'm interested in here is quantizing this system. So I want to do quantum gravity in this framework. And here again, there's the Lagrangian. Now I've eliminated the potential term because the region that we're interested in, the potential is just zero. So we have to study this Lagrangian in this billiard domain, which is the wedge or the cone that I showed you before. And here is the metric written out, and we have to also implement that these beta variables are oriented in a null direction in beta space. So this is a very simple problem to quantize. You just go to the canonical momenta, PA, and you write down the corresponding Hamiltonian, which is just p squared with the inverse metric now. And that means that the corresponding quantum problem you have to solve now, the Wheeler-DeWitt equation, is just this operator here acting on the wave function equal to 0. And G is a constant matrix. So, so your Hilbert space would be the space of all these functions of the betas. You can define some inner product, which is not really positive definite, on that space, and you look for solutions of this equation. This is the quantum gravity problem in this context. Now I will want to give some more details on the solution, because it turns out it has a nice mathematical structure. The easiest way to analyze this this metric now is by using adapted coordinates. So you take, we're inside the forward light cone, so you take coordinates where you have a unit hyperboloid and sort of a radial direction. Or I think I have another picture for that. So here, so this is a cross section, this is a unit hyperboloid, and there's one radial direction. And in these variables now, you can rewrite this differential operator in this language here. So you have just rho, which is the radial part, and the singularity in these variables sits when rho goes to infinity, and there's some remaining part which is just the Laplace operator on the unit hyperboloid. So this has some standard expression. So this is the equation now you have to solve. And here it is again. And one easy way of solving it is by separating the variables, because the differential operator does separate nicely. And by assuming you have an eigenfunction of this Laplace operator, you can immediately solve for the radial dependence. And you just get some function. In fact, you get two functions, because it's a second order differential equation. And using the inner product that I had before, you can identify one of them as being positive frequency, and the other one is negative frequency. And if you restrict to the space of positive frequency solutions only, you have a true Hilbert space. So now all that we need now, I mean, we've solved for the radial dependence or the rho dependence. Now we need solutions of this equation, and this is sort of the core of the subject. So we're looking for solutions of the Laplace or eigenfunctions of the Laplace operator on a hyperbolic space. And to parameterize this, it's convenient to use an upper half plane model. So the upper half plane model for hyperbolic space has sort of, in this case, d minus 2 directions here and one which is sort of related to the upper part. And the Laplace operator in these variables here now takes this form. So there's just the flat operator in the d minus 2 spatial directions, and then there's the special direction which has additional properties. Now, now it is important when you solve this spectral problem that you specify the boundary conditions properly. And I said before, we want to study this problem where we are on the billiard domain. So what you would want to do is, you have infinite potential walls, you put Dirichlet boundary conditions at the edge of this billiard domain. So this is now the intersection of this wedge with a unit hyperboloid in this upper half plane model, and you put Dirichlet conditions on the boundary. And this completely specifies the spectral problem, and it is already sufficient to prove something about the spectrum now, because you can show that the spectrum is bounded from below, and it satisfies this, well, with a minus sign, and it satisfies this inequality. And in fact, this is more or less all that you can extract immediately. So beyond this general inequality, the detail of the spectrum depends on the shape of the domain. I haven't yet used that there is some group theory determining the shape of the domain. And
Axel?
Yeah.
What do I learn about the physics of things from the spectrum in this sort of reduced context? I mean, so you do some calculation, you go, okay, I've got a spectrum, this one-dimensional problem.
Yeah.
What does that tell me about space-time?
So, for example, it would tell you, is there, okay, let's go back to here. So this is, so the spectrum sort of enters, for example, here in this radial dependence. So it will tell you something about rho. Now plays the role of the time parameter. I said that singularity sits at rho goes to infinity. In quantum gravity, I mean, the relativity equation is timeless. You have to introduce some effective time, and in this case it's played by rho. And for example, you can see, depending on the value of E and which sign you choose here, the limit rho going to infinity will depend on these details. So this is already something that we will discuss later. And that's sort of the crudest information that you can extract from that. Otherwise, you might be interested in, for example, the question, is there a gap in the spectrum? So is there some kind of natural ground state? What about the transitions? Now, where was I? So yes, so beyond this general inequality, I mean, there's not so much known. Now I want to come back and focus on maximal supergravity, which is this, where the domain is determined by this E10 group, and here I've drawn the Duncan diagram for E10, so you can see it has sort of the nodes which are labeled 1 up to 8 as just the E8 part, and then this is a very special extension of the E8 group. So if you go include the node 9, you get affine E8, which is also sometimes called E9. One more gives you E10, which is this hyperbolic Kac-Moody algebra, and an associated hyperbolic Weil group. And if you're in this context, it's very convenient to use octonions to parameterize the whole problem. So this might seem just like as a mathematical curiosity now. But it turns out that basically all these hyperbolic Weil groups, they have a very nice interpretation in terms of division algebras. But this is not something that I want to explain in more detail. Let's just use octonions for the 8 sort of horizontal directions in this 9-dimensional hyperbolic space, and then V is just a real number which goes in the other direction. So the 9 dimensions here are 8 octonions and just a real positive number. This group here, the Weil group, is generated by 10, because there are 10 nodes, fundamental reflections. And here I've written out how these fundamental reflections act on this variable z if you use this octonionic language. And they take a very nice and suggestive form. So there's like a 1 over z bar because it's a reflection, and then there's like a minus z bar plus 1, and then there's some kind of rotation matrices. But there's always a bar here because the determinant of these transformations is -1, so they're not holomorphic. And the rotations here, they depend on how you embed E8 in here in the octonions. Now, if you do this, so these are the same transformations, and iterating this will give you the whole Weil group of E10. Now, you might be a bit worried about this bar here, and in fact you can get rid of it by restricting to the even part of the Weil group. And the even part is only when you do 2 transformations, or multiples of 2 fundamental reflections. Now, if you do this, you get rid of the bar and you get holomorphic maps, and in a very natural sense, this even part, which I call W plus of the Weil group of E10, you should identify this with the group PSL2 over O, and this O here, which looks a bit different from the O I had before, is just the integer subset of all the octonions. So you have like, it's not PSL2 over the rational integers Z or Z, but it's over the octonionic integers. And this is now the modular group which enters in the description of our wave function of the universe. And as I said, this is sort of just the tip of the iceberg of some very general story of isomorphisms between some hyperbolic Weil groups and other things. But staying with this, now we have to come back to the boundary conditions. The boundary conditions, whether they're Dirichlet or Neumann at the boundary of the domain, just is now related to how you extend this PSL2O function to a PGL2O function. So you have to say, how does a single, when you have only one fundamental reflection, how does that act on the coordinates? And either you can choose plus or minus. Minus sign is a Dirichlet condition because that means that the boundary which is left invariant by the reflection, the function is odd, so it has to vanish at the boundary. So this is the right kind of conditions. And then we have this function which is defined only on the fundamental domain, and we can use the symmetry to unfold it to a function on the whole space. So this is where the automorphic property comes in. So at the end of the day, you have some function psi, which is defined on the whole hyperbolic space, and it has the following properties. So it's a sum of eigenfunctions of this Laplace operator. It is invariant under the action of this modular group, and it's anti-invariant under the extension to the full Weyl group. And in mathematical terms, all what this is saying is that this wave function is something what is called an odd mass waveform. So mass waveforms are eigenfunctions of the Laplace operator, and odd refers to this minus sign. So now I've completely reformulated the problem of quantizing gravity in this toy context in terms of some mathematical theory of automorphic forms. So you might go, hey, this is nice because now maybe we can use some mathematics papers to actually learn something about the physics. But now the bad news is that the spectrum is not known. So now we've identified the precise objects that we want, but we still don't know exactly what the functions are and what the spectrum looks like. But there's very good reason to suspect that it is discrete, because these are like cusp forms in the SL2 case, so that's also part of the discrete spectrum. But this theory is not well developed in the mathematics literature.
Let's ask a question, it's a sensible question. If you, instead of the octonions, you looked at the quaternions as a model, I mean, as a simpler example. What are these?
So the quaternions, they arise for a six-dimensional theory. And wait, am I saying this right? So they arise for a specific six-dimensional theory, which is just sort of the type 1 theory in 6 dimensions. So it's not related, to any of these superconformal models. It's a supergravity theory, which has a certain number of vector multiplets.
But the automorphic form that you get is something familiar, is it, in some other?
So for the octonions, there's more work in the mathematics literature, but strangely enough, most people are not so much interested in these mass waveforms, but there's more work on the Siegel generalization of the modular forms to other groups, to other integers. So sort of SP2 over the quaternions or octonions, this is something that people study more than this SL2, TSL2. Okay. Now, so in lower dimensional cases, when you don't have the octonions but some other numbers like the usual integers, there's more work, and in particular there's a lot of numerical work done studying the spectrum of these forms, and I just give some references. But the only thing that I will want to discuss now is the fact that we have this general inequality that we could deduce just from the property of imposing Dirichlet boundary conditions. So this is something that I just summarized in words already. So this quantum billiard wave function is this mathematical object. So now if we use this inequality and go back to the solution for the radio dependence for this function r that I had before, you can see that this will imply, let's go first down here. So this is the radio function r. If you now plug in this general inequality, you will see that this argument of the square root is positive. So this means that this radio function as rho goes to infinity, first of all it goes to 0 because there's a damping term, but it keeps oscillating. So you have this means, because the psi is a product of these things, the full wave function will go to 0 as you go to the singularity, but it will oscillate. And this has some maybe physical significance. But maybe I should say first what I wrote on the top of the slide. So if you now want to study the wave function not only of one point, because I said this is an ultra-local analysis, but you want to study it for the whole space-time, so you have to take a product of wave functions for a given point. So psi x is a wave function of the type I just had now for one point, which is completely decoupled from all the other points. The wave function of all points, because there's no interaction, is just the direct product of all these wave functions. And that's a consequence of ultra-locality. So this would be the full wave function of the universe, which is a very crude model.
I'm going to this is naive. Surely the phase of the wave function doesn't matter in physical things if I can't do interference and so on. I mean, what do you really mean when you... I mean, what physically are you going to use this wave function for? Because, I mean, normally with wave functions, I don't worry about the phase, right?
So, of course, you worry about the phase when you do interference, as you say, but I mean, you don't want to sort of interfere universes.
You can't interfere.
Yeah.
No, you can't.
So what you could use this for is to define, for example, an arrow of time. So I said before, depending on which sign you choose, you will have positive frequency or negative frequency. So you certainly need sort of this oscillating phase to say which are the positive frequency modes that come out of the singularity. And this sort of tells you when is earlier and when is later. I mean, this gives you an arrow of time. This is something that you could use this phase for.
I'm worried I can't measure it. I mean, so though you're defining something there,
Yeah.
I'm worried I can't ever measure it.
So, I mean, okay, I should also say, I mean, I said the inner product on these wave functions is this Klein-Gordon inner product. The Klein-Gordon inner product, for example, has the property that it vanishes for real wave functions. So if you set the wave function to 0, this thing would have 0 norm. So you certainly need the phase to have non-zero. I mean, you need to have a complex wave function to start with to have non-zero norm. And then you need the right sign here to have positive norm instead of negative norm. So that's what I mean with positive frequency and negative frequency defining the Hilbert space. So you do need this phase, you can't just ignore it. Because the inner product is, I mean, sort of you have psi, star,
Okay.
deep psi, sort of this is the, and
Okay,
you integrate this with the right measure. So you have psi. And this is the inner product. So if you have a real function, then you can see that this goes to 0.
Okay.
So we do need to worry about the phase. Okay, but so there's something that is, although this is a very simplistic model, there are some nice features of it and some not so nice features. So let me first talk about the nice features. Because there's no potential, first of all, there were no ordering ambiguities when setting up the quantum problem. And secondly, what we got was a well-defined Hilbert space with a really positive definite metric. And this is something that is not so easy to come by when you do canonical quantum gravity. Another property that I already pointed out was that the wave function vanishes as you approach the singularity. But it does so in a way that it is oscillating all the time and stays complex all the time. So this is maybe something that could have a physical interpretation, this property here. So the fact that it goes to 0 evenly, sort of it smoothes out very nicely, homogeneously, this could be interpreted as the absence of a bounce. I mean, there's no indication in this setup that there will be a bounce when you go to the singularity. And another thing is that already in the early days of canonical quantum gravity, Bryce DeWitt suggested that how do you get rid of singular geometries, or how do singular geometries get resolved in quantum gravity? And he said, well, the most plausible thing is that you have a vanishing wave function on the singular geometries. And this is something that is realized here. So I'm not claiming that this is something that I fully subscribe to, that this is the right way of resolving quantum mechanically the singular geometries, but this might be one possible solution. This is something that I just discussed already in answer to your question. So there's something which is related to the arrow of time, and that's work of Aish. Yeah.
This vanishing here, that's not related to that you chose Dirichlet boundary conditions for the wave function, and that was it.
So I mean, it's a consequence of choosing Dirichlet wave functions, but I didn't choose the Dirichlet wave functions at the singularity. So I chose the wave function at the boundary of this sort of Weil chamber, which is, I mean, the shape of that and the position of that is in the auxiliary space of radial direction, and that's not related to the singularity, to the geometrical directions. So I didn't impose that from the beginning, but it's a consequence over the spectrum of the Laplace operator. And and maybe finally I should say you can ask yourself sort of what happens to semi-classical states in this context, and of course because there's not so much known In analytic form, this is something you have to do mostly numerically, and there's a lot of work on that. I just give one reference. What you see in these numerical investigations is just what you would expect, namely that these semi-classical states, they start to spread. So if you take some wave packet where sort of the universe is initially localized in something that is looks more like a classical universe, so you have very well-defined expectation values for all these radii. As you go to the singularity, this thing just spreads out and it sort of fills all possible states, and it's in term quantum ergodicity. I mean, in general, as I was saying, the classical system is a chaotical system, so that's related to the question, how does classical chaos relate to quantum chaos? And quantum mechanics is always unitary, so there's some issue directly with chaoticity, but the closest you can get typically is quantum ergodicity, and that seems to be realized in this quantum system. Okay, so maybe I'll just briefly say, before I move on to other things, one example of one of these Mars waveforms that you can explicitly write down, so to show you that I'm not only doing sort of Gedanken mathematics, but really proper mathematics. So you can define some invariant function by using this expression here, which looks very familiar from PSL2 over the usual integers. So you just take an element on the upper half plane, you act on it with an element of the symmetry group, and then what you do is you take sort of the component along the cusp direction, which I called here, which is called V, and so I is just the projection along the cusp, and you raise it to some power. And you can show on general grounds that this defines an automorphic function with a given eigenvalue of the Laplace operator. I think it's s times 8 minus s or so in this case. And this is just a function you can construct, and you can also rewrite this function in a more familiar form using these octonionic numbers that I mentioned before. So it looks exactly like the rational case where you sum over co-prime numbers, and here you have to be a bit careful how you define co-prime, because the octonions are not commutative and they're not even associative, so you have to be a bit careful what this means. But if you define this properly, you just end up on the same definition that you have normally. So this is just to show that you can construct eigenfunctions of this Laplace operator. So this would be some potential, well, it could be some potential wave function of the universe, this Poincare series, or maybe you want to call it Eisenstein series rather. The only drawback of this thing is that it's part of the continuous spectrum. I mean, S is just any real number, or maybe even complex number if you analytically continue. And it has Neumann boundary conditions and not Dirichlet boundary conditions. So this is not in the right part of the spectrum, but it's certainly some automorphic function.
So can you remind us what the Neumann conditions applied?
So the Dirichlet conditions were there because we had these infinite potential balls, and they implied that you have to be in the discrete spectrum. And if you work this out for this guy here, you find that it has Neumann boundary conditions. So that's not the right part of the spectrum that you want to study. But at least it's some automorphic function of this fancy modular group. And yeah, and here's some further properties of it. So you can now take this and get rid of this coprimality constraint by introducing some kind of zeta function, which is now a Dedekind zeta function. This is maybe not so interesting, all the details. I'm just showing this to make sure that this is not empty. I mean, I'm not talking about the empty set. There are things here that you can do explicitly. Okay. Let's not go more into this. So now this was a very simplistic model. Now I would like to generalize this in two different ways. So first I will try to generalize the cosmological billiards setup, and then I will try later to generalize the automorphic forms part of this. So let's start with the cosmological billiard.
Question.
Yep.
So this automorphic form is a wave function on some moduli space, right? So
Yeah.
this includes also the dilaton. So do you know that you stay at weak coupling?
So this was not on the full moduli space, but only on the moduli space sort of radii. And then in the radii, so if you take 11-dimensional supergravity, compactified on a 10 torus, so the 10 radii there. Of course, there's some combination of that you could interpret as a coupling, as string coupling, by dimensional reduction. And the expansion that I've shown here, this is sort of the weak coupling expansion. So this, when I started out with cosmological billiards, I said that the structure is very much determined by E10, by the structure of E10, and this has led to the so-called E10 conjecture. And this conjecture, which by now is maybe 10 years old, says that you can capture more of supergravity. So if you want to go beyond the ultra-local approximation, you want to also say something about how the different spatial points interact, you should go beyond the billiard picture, but instead study some infinite dimensional space. And this infinite dimensional space should be sort of the generalization of the moduli spaces in higher dimensions, and it should be E10 divided by its compact subgroup. And you want to study null geodesics on this space. In fact, constrained null geodesics. So if this is a cartoon of the of the infinite dimensional space, and this is some null geodesic in there, any such null geodesic by this conjecture should correspond to a solution of d equals 11 supergravity, which may or may not be a black hole. And so this is a natural conjecture in the sense that this symmetric space has a very nice decomposition into 10 plus infinitely many directions, and the 10 here, which is related to the 10 there, is immediately the number of 10 radii in the cosmological billiard. So this is just an extension of the cosmological billiard picture by including also these infinitely many other directions in this space. And as I said, the idea is that these infinitely many other directions that you have, they should be there to say something about the non-ultra-local behavior. So they should say something about the spatial dependence of your supergravity fields. You want to go beyond only time dependence. And this is something that has been verified for a few of these infinitely many things. I mean, this is hard to prove in general. And there it worked quite well, but there are some problems when you sort of want to push the calculation further. But at least, I mean, this sort of as an idea, it doesn't look completely absurd. And how this works is that the space dependence gets introduced via dualities. Because, let me go back to this slide here. So, I mean, this geodesic only depends on a single parameter. There's only t, which is sort of the parameter along the curve. And now you have to say, how do you translate this t into all the different spatial coordinates? And the way you do this is by saying, okay, a certain direction in this space, which is t-dependent, in fact, by some kind of Hodge duality, is like a spatial dependence of a different field. And that idea seems to work very well at low levels, and it also ties up with things that are known from integrable models in gravity in 2 dimensions related to the garage group. And I have to say, one of the features of this idea that I find nicest is the fact that, I mean, you've completely eliminated geometrical space, but you've replaced it by something that is a completely algebraic object. So by doing algebra in this very complicated symmetric space, using the properties of E10, what you can do is you can try to reconstruct space. And the good thing is that, I mean, this thing here doesn't really know anything about whether you talk about 11-dimensional supergravity, type 2a supergravity, generalized geometry, anything like this, because this is just a different way of analyzing this symmetric space by choosing different bases for the field. So you can combine all the possible geometries in all the different dimensions, all the different kinds of maximally supersymmetric theories, by just reinterpreting this space in a different basis. So this is a very unifying picture that you can have in this way. And yeah, so as I said before, this overcomes the ultra-local part. of the cosmological billiard, and it seems at present that even though you're talking about an infinite dimensional space, most of these the directions are auxiliary fields, so at the end of the day the only propagating degrees of freedom that you will describe in this way are just the supergravity ones.
So what does that mean?
So that means that in the early days of this conjecture it was thought that this is, the 10 coset space in the null geodesics would be something that actually relates to M theory and string theory degrees of freedom. So for example, if you rewrite this in a basis which is adapted to type 2a supergravity, there are sort of the supergravity fields and infinitely many more. And people thought maybe among these infinitely many more, there are like the massive string states of type 2a superstrings. And what we're thinking now is that this is not true. So all these additional fields are just auxiliary fields that you can use to rewrite the type 2a dynamics in a nicer, more covariant form, more symmetric form, but there are no massive string states or other states.
This is meant to, this is in some sense meant to capture quantum supergravity.
So this is, I'm still at the classical level now at the moment, yeah. So later on I will say, of course, you want to quantize this in the same way that I quantize the cosmological billiard, but yeah. But this, yeah, so this statement is just saying that there apparently are no massive string degrees of freedom contained in this picture. Yeah.
Maybe, it's a related question. We had the thing before where we quantized, and I guess I'm trying to understand, we know that gravity's got divergences in that we can't cure without, say, the inclusion of string states.
Mm-hmm.
So how are you curing the divergences without the inclusion of string states?
So, so there's one thing, so this is a classical picture, and at the moment there are some issues here showing that this is completely equivalent to supergravity. So it might be that this model deviates slightly from supergravity, and then of course it might have slightly different divergences if you do the quantum theory.
So that could be a regularization, effectively. in
Yeah.
some sense, that's special.
Yeah. But this is a very speculative idea because it's very hard to work this out, but I think there's some room for this. Okay, so if you generalize this, before we had this sort of billiard Hamiltonian, which was just pi squared, and now if you go to the full coset model, by including all these infinitely many other terms, there's a unique extension of this billiard Hamiltonian to something which is invariant under the full E10 symmetry, and not only under the Weyl symmetry. And this still looks very much like a simple system because it's like a free Klein-Gordon system. There are these scale factors here, but it's just pi squared plus pi squared. Maybe it could be that this sort of positive norm restriction we had before still remains consistent here. But something that I would like to stress is that this is really the unique extension that you have for this thing. So by demanding the symmetry structure, you're automatically forced on, at least at the two derivative level, so this is a quadratic thing, at a unique expression for the Hamiltonian. So the full theory has more constraints than just the Hamiltonian, so there are the diffeomorphism constraints, Gauss constraints, and so on. And all these should be I'll go to the other side.
Has everyone switched their phone?
It's not mine.
Yeah, Wi-Fi, anything transmitted with mic.
Does interfere somehow.
Wi-Fi. No.
No.
Anyway,
All right.
okay, I'll just speak up. And so the idea is now that here you all have all these infinitely many constraints, or the additional constraints, diffeomorphism and so on, that you have to implement on the wave function. And it's also here that the symmetry could be of help. So because this global symmetry, it's a global symmetry, this provides conserved charges by Noether's theorem. It's an infinite dimensional symmetry, so you have infinitely many conserved charges. And maybe all these constraints here are just restrictions or constraints on these charges. And there's some evidence that this is true and that all these constraints, like this one is quadratic in these j's, and all the other ones, they can also be rewritten sort of as a current times current or j times j form, which looks a lot like the Sugawara construction. So it might be that there's some generalization of the Sugawara construction to E10, and maybe this is something that will be useful when quantizing this full geodesic model. So this is AIM, which means it's an open problem. It's something that has not been done. But I think this structure here could be very useful in the same way that, I mean, if you quantize the usual bosonic string or the superstring covariantly, I mean, implementing the Virasoro constraints, now you want all these L's to vanish, is very important for getting the right spectrum and the right model. And in particular, like a no-ghost theorem and so on. So maybe this will, I mean, say something about the quantum issues. So now I promised you 2 generalizations. In the last 10 or so minutes, I want to talk about something slightly different. So I want to generalize the aspect of modular forms. So I said before we had these mass forms for this PSL2 O, which was the Weyl group of E10, but I mean there's very good evidence that what is relevant in string theory is not really the Weyl group, but actually sort of the full discrete subgroup of the global symmetry group. So if you believe that the global symmetry group is E10 over R, the natural extension or guess for the duality group would be E10 over the integers, where you have to be a bit careful how you define this using some Chevalier relations and so on. But this is something that has been mentioned many, many times in the literature. So this is what should be the quantum symmetry. So this object should control the quantization of the full coset model. And for smaller rank, of course, this is very closely related to the study of automorphic forms, say in scattering amplitudes and effective actions, which has been done for E6, E7, and so on, and has led to all this beautiful work on instanton corrections. Now, the question is, when you go to this group instead of this group, what can you say about its automorphic objects? And it's known that for the smaller rank cases, the objects that appear in all the quantum corrections are Eisenstein series for E6, E7, and so on over the integers. Now, it seems natural to ask the question, what about Eisenstein series for E10, or maybe to be a bit more modest, E9, which is also infinite dimensional? And this is now what I want to say in the last part of the talk. So, unfortunately, again, there's very little literature on the subjects in the mathematics community. There's some work by Garland. I mean, this is sort of the first paper, but there's a big series of papers which deals with the affine case, E9. And just for completeness, I've written here the definition of the Eisenstein series for E9. And it looks exactly like you would write it for E8, E7, and so on. So it's a sum over, so it depends on the group element. So G is an element of E9. You take this element, act on it with something from the discrete group, gamma, project it back to the Cartan subalgebra, and then take its inner product with a given weight vector, and this weight vector specifies the Eisenstein series. One complication for E9 is, because it's affine, the Cartan matrix is singular, you have to put in an additional variable R, which is associated with the derivation. But this is sort of just a technical improvement or modification that you have to do. Otherwise, it's exactly the same expression as for finite dimensional ones.
What do you mean by the derivation? You mean you expand the affine algebra by including...
So normally, I mean, if you do the loop algebra, you just have a Laurent series in the usual algebra, and then there's a central element, and then there's a D, which is sort of D by the spectral parameter. And this is the one, I mean, the sort of the C has norm 0, so the inner product on the Cartan subalgebra, and this is sort of that D singularizes this. So C is the null direction, and D is the other null direction.
Yeah, so it's the values within a product.
Yeah. So this is something you have to throw in, that this becomes well defined. Yeah. Yeah, and often it's called derivation, but it's, yeah. but because it really acts as a derivative on the spectral parameter in the loop algebra language. Okay, yeah, so this is now the formal expression here, and what people have also studied is how to sort of decompose this very complicated object in terms of different parts. And one of the most important parts whenever you have an Eisenstein series is the so-called constant term. And the constant term in string theory language is what gives you the perturbative terms in the expansion. So the constant terms are the ones that are just sort of polynomial in the string coupling, and then there are non-perturbative terms which are also part of the Eisenstein series, which are related to instanton corrections. So this, what I'm now discussing, is only sort of the perturbative piece of this, or the perturbative information encoded in this Eisenstein series. And what is known is that for these Eisenstein series there's a very general formula. So here there should be an equal to constant terms. This is what the constant terms or the perturbative terms look like. So there is sum over the Weil group with some coefficients, and then this is sort of just the Weil rotation of the string coupling projected back onto the Cartan subalgebra. So in the easiest case, I mean, if you were in SL2, maybe I should say this to make this a bit more transparent. In the easiest case for SL2, the Weil group is just two elements, either identity or reflection, which then will give you either string coupling or sort of 1 over string coupling. And if you convert this back, so this is an Einstein frame, if you convert this back to string frame, what you find is just the tree level and the one loop term in the perturbative expansion. And these are exactly the two terms that are known from non-renormalization theorems to exist for type 2b supergravity for graviton scattering. I mean, it's very well known. And this is just the generalization of this expression as a mathematical theorem to the larger groups. And this sort of coefficient that appears here has some mildly complicated form, but not overly complicated. So it's a product over some positive roots with a certain condition. And this psi here is basically the Riemann zeta function dressed up with gamma factors and pi factors. Something called the completed Riemann zeta function. So this is something that is very explicit. It's not completely straightforward to evaluate, but you can do it. And now you might immediately say there's a big problem here, because I said before for SL2 there are only two terms in the Weil group. If you go to infinite dimensional groups, the Weil groups are also infinite order. So that means that this sum here is a sum of infinitely many terms, which would mean you have an infinite number of perturbative contributions to, if this is computing some scattering amplitude, to your scattering amplitude. And this is not what you want and what you would expect. So what comes to the rescue now is that this sum here collapses to a finite number of terms if you choose lambda correctly. So lambda appears here in this coefficient, and if you choose lambda correctly, most of these factors will be 0, so this infinite sum just gets restricted to a finite sum. And these are exactly the cases that are interesting in string theory. So for example, if you choose this lambda here, which determines the Eisenstein series in this form, 2s minus some fundamental weight capital lambda I minus the Weil vector rho, this collapse can only happen if 2s is an integer. And all the Eisenstein series that have occurred so far in string theory are exactly of this type.
Integer or odd integer?
So 2s has to be, so the ones that have appeared are odd integer, but this collapse can also happen when it's an even integer. And I'll show you a table in a second where you see some of these collapses. So this is proved rigorously for affine E9, and I think it's plausible to assume that it's also valid for E10, because this is just the same expression as for E8, E6, and so on. So there was nothing happening when you go to the affine case, and probably there's nothing happening when you go to the hyperbolic case. So now you can analyze this collapse, and here I've shown you a few cases. Up here again is the Duncan diagram of E10, and now the first question is, how do you choose this lambda I that you want to study? And I will choose it to be the one that is associated with this node back here, and there's a very simple physical reason for doing that. If you delete this node from the Dynkin diagram, you're left with a ODD diagram. So this is sort of T-duality, which it becomes the discrete T-duality, ODD over the integers. And you know this is a perturbative, I mean this is an exact symmetry of in perturbation theory in alpha primed or string theory. So these Eisenstein series appear at a fixed order in alpha prime, say alpha prime cubed, for graviton scattering, something like this. And certainly you want to have something at this order which is T-duality invariant. So you'd better construct your Eisenstein series in such a way that it respects the T-duality invariance. And the only way of doing this is by selecting this node back here. So this sort of gives you a physical reason for selecting this node. And then the only thing that you have to worry about is what is S. And S, I said, should be such that it's half integer, or 2S is an integer. And I've just listed the number of summons in this constant term in this table. So for completeness, here are the known cases for E7 and E8. And you can see that, I mean, there's a big collapse of the number of terms. Especially when you go to 3 halves, the number is very small, and there's some nice pattern as you go up with S. But most certainly, out of these infinitely many terms that you could have in general, and S equal to 1 sort of, there's nothing special happening. You see that you get very few terms only. And you can do the same thing for E11 if you want, so the formalism works the same way.
So sorry, just so I understand, the number of those numbers, the number of terms in that sum?
Yeah, so these numbers here are the number of non-zero summons in this infinite sum.
Uh-huh.
So, I mean, for E, let's say for E8, if you go back to E8, the while group has, I don't know, like 700 million elements or something of that order. If you choose this particular lambda and this particular S, only 9 terms are non-zero. If you go to E9, there are infinitely many things. If you choose this lambda and this S, there are only 10 terms that are non-zero. And I mean, you cannot only determine which terms are non-zero, but you can also work out explicitly, because here you have a very explicit expression for computing the coefficients and sort of the moduli dependence. I mean, you can work this out explicitly. For that purpose, I'm showing here sort of the constant term in this expansion for the case of E10, and you take S equal to 3 halves, and I should say S equal to 3 halves is the case that is relevant for R to the 4th. And I'm in the minimal parabolic here. Yeah. So you can see a number of, you see like 10 radii, R1 up to R10, that appear here, which are related to the radii of the torus, and there's some complicated dependence on them. And in fact, there are some terms that are sort of divergent. If you take the limit properly, you get sort of these logarithms, and not only rational dependence on the radii, you get some, from the limit you get some, so this comes from the gamma functions that enter in this psi function, you get some constant pieces and so on. So maybe this is sort of the first threshold term that you would normally have in the decompactification. So there's some general feature how this term here relates to the Eisenstein series, not of E10 but for E9, and the relation uses some sort of threshold term, and this is exactly this term. So this appears in the same pattern. So this is so this goes to show that it's possible, and I think that's something that has not been done in the literature to the best of my knowledge, to analyze these Eisenstein series for affine and hyperbolic groups, and to study the behavior or special values of lambda where special things happen with these functions. And it turns out that the values of lambda that are special in string theory are also such that, let me go back here, very special things happen for the number of constant terms. So this is, I mean, as I said, the constant terms are sort of only the perturbative part of this object. There are non-perturbative corrections, which are sort of non-zero Fourier decompositions in the mathematical language. And they come in 2 varieties. There are abelian Fourier coefficients and non-abelian ones, and all these 3 terms together make up the full Fourier decomposition. And this is sort of only the tip of the iceberg, but in some sense this contains a lot of physically interesting information already. And so this just shows that, that you can study these objects. Okay, let me summarize. So I've discussed a number of vaguely related things. So I started out with a quantum cosmological billiard and how the automorphic forms for the octonions enter. I didn't show you how to extend this to the supersymmetric case, but that can be done too. Then I've shown you these modular forms for E10 and also these Poincare series for the Weyl group, and analyzed parts of them. And yeah, so that's what was in the talk. And of course, there are many things that are not in the talk, and mainly because they're not done yet. And that is to construct these wave functions more explicitly with the right boundary conditions, to understand better the full coset model and the constraints, observables, quantization, and all these things. And also to get even a better understanding of these modular forms for E9 over the integers E10, and how they relate to physical quantities in some scattering processes of strings. And that's it.
Question. Yeah. I know that for the automorphic forms based on like finite groups, SL and SOP and ABC, you rewrite them in terms of the sum over lattice.
Yeah.
Can you do that for your E9, E10?
So, I mean, already for like E6, E7, and E8, there's a problem with doing that. And I mean, okay, I should say this differently. So already if you do it for SODD, you can write it as a sum over the lattice, but what you find is typically not an eigenfunction of the Laplace operator.
Right, but if you put a constraint in.
So you put an additional constraint, which is sort of half BPS constraints in physical terms, to make it an eigenfunction. So for E6, E7, and E8, there's some, you can try to do similar things, and that's partly the content of the last paper that Michael wrote with Pierre van Hove and Steve Miller, so trying to identify the charge lattice and what you sum over. And I have to say, I'm not completely sure, but I have the impression that this has not been settled completely, this question. And also in this case here, I don't know if you can do that.
You even do it for just affine SLN, you know?
Yeah, I mean, you would have to identify the proper charge lattice, which might be infinite dimensional in this case. So that's, I think that's not the right way of defining the series.
I'm just curious about your energy bound for the Laplacian there. Do you know if it happens to be related to a so-called Hardy inequality?
So I don't know what the Hardy inequality is, so it's hard to say yes or no.
No, because it's usually of exactly that formula, D minus 2.
Okay, so maybe you can explain to me what the Hardy inequality is, and then afterwards, and then we can see if it's the same thing or not. Yeah.
Okay. So if you could